For my project, I decided to explore the most prominent form of math in video games, vectors. Although they represent simple concepts of position and direction, they are used everywhere. They are used for physics handling, collision detection, movement, AI pathfinding, and much more. Instead of just doing research, I decided to code my own billiards ball game from scratch using vectors and 3.js. 3.js is just a JavaScript library to render the graphics of my pool game, and everything else, such as the physics, game logic, and 3D models, were made from scratch. I first modeled a pool table and a pool cue in Blender to use as assets for my game. After playing around with some lighting and post-processing, I was pretty happy with the scene I set up. The first thing that I did was to create and spawn the billiard balls in. I wanted them to spawn in a triangle shape and also be as close to each other as possible without overlapping. I decided to do this with a nested for loop. I would place the initial ball with a predetermined vector position. Then the outer for loop will place the leftmost ball of each row, and the inner for loop will place balls along each row. So basically, the spawn order should look like this. For balls in the same row, we can find their position vectors simply by adding the diameter of one ball to the previous ball's x component. To spawn diagonal balls, we need to know the value of both the x and y offsets. Again, the diagonal is just the diameter of the ball. We can also see that the x offset is just the radius. Since this is a right triangle, I then used Pythagorean's theorem to find the y offset. Using these two offset values, I created a direction vector that points in the left upwards direction. And the magnitude of this vector I created is equal to the diagonal offset of one ball. Using a for loop, I multiplied this vector by 0, 1, 2, 3, and 4 to get the position vectors of these 5 balls. And then I added some code to randomize the colors while still keeping the black ball in the middle. Next, I started to implement physics, starting with movement. Each ball was given a velocity and a position vector when they respawn. Therefore, I just need to add the velocity vector to the position vector every delta second that passes. This updates their position and creates what looks like movement on your screen. I then set up collisions with walls. This was pretty simple as I just had to set up some if statements to check if a ball has passed the left, right, upper, or lower bounds of the pool table. Once the ball does cross those bounds, I just have to reverse the x or y component of the ball's velocity depending on which wall it hits. For example, if it collides with the right wall, it maintains its y velocity while the x velocity is reflected. And then I gave each ball a random velocity to test if the bounds are actually working. Handling ball collisions with each other was a bit trickier, so I'll be showing an example while walking through my code for a clearer explanation. First, even without math, intuition tells us that after colliding, these balls should bounce in these two general directions. Let's check if the math works out. My code first calculates a collision normal, which is the direction the balls will bounce off from each other. This is done by subtracting the position of ball 2 from ball 1, giving a vector pointing from ball 2 to ball 1. In this case, the normal is -2, 0, and I normalize this vector to preserve the direction while removing the magnitude. N is now -1, 0 after normalizing it. I then split the ball's velocity into their normal and tangential components. I did this by multiplying the normal with the dot product between the ball's velocity and the normal. Remember, the dot product tells us how much of the ball's velocity is in the direction of the normal. Since the normal is normalized to unit 1, scalar multiplying the dot product will give us a vector with the proper direction and magnitude of the normal component. This vector is essentially the part of the velocity that will be colliding with the other ball. The tangential velocity is just the component not involved with the collision. To get this vector, I just subtracted the ball's original velocity by its normal component. To handle collisions, I swapped the two balls' normal components while keeping their tangential components the same. This way, they bounce off of each other while retaining their velocity in any direction unrelated to the collision. I first did this graphically by drawing out the swap normal vectors. Adding the newly drawn normal and tangential vectors will show the velocity of the balls after they collide. Just by looking at these new velocities, this aligns with our initial intuition. Mathematically, the vectors also check out if you add the swap normals and original tangentials. The example I used was really simple for the sake of visual clarity. Since the collision normal was along the x-axis, the normal component is just the x value and the tangential component is the y value. However, this method still works for any possible angle or velocities that the balls will collide in. I then added the cue to hit the ball with. I originally set the cue's position to the white ball's position and I would just rotate the model. However, all billiards games have an offset between the cue and the ball. The simple solution here was to go into Blender and artificially offset the model from its object origin. However, this would make things a lot harder later, so I decided against it. Instead, I opted to create a sine and cos function that would describe a circle that the cue should move in. Combined with rotating the model orientation, it would look like the cue is rotating around the white ball at a fixed offset. Objects moving in circles really just have oscillating x and y coordinates. In my code, I originally spawned the cue with a fixed y offset of -0.1. This means the cue will orbit along a circle of radius 0.1 when rotating around the ball. It also means the amplitude of the sine and cos functions will be 0.1. The x-coordinate starts at the center, 0, moves to -0.1, then 0, then 0.1, then 0 again. This is a negative sine function. The y-coordinate starts at -0.1, then 0, then 0.1, and then 0. This is a negative cos function. Remember, these coordinates are all relative to the position of the white ball. Let the position vector of the white ball be n. The position of the cue can now be described as this formula, where the r value is the rotation of the orientation of the cue in radians. For example, let's say the white ball is at 0, 0 for simplicity. The cue starting rotation is 0 radians. When plugged into the formula, the cue's position should now be 0, -0.1. When the cue rotates -90 degrees, its position is now -0.1, 0, and so on for every angle. This code here changes the angle of the cue by 100th of a pi corresponding to the arrow key pressed. Since the actual position of the cue is now offset from the position of the ball, hitting the white ball was pretty easy. I just subtracted the position vector of the ball from the cue, which gave me a direction vector of where the cue was facing, thus where the white ball should move when the cue hits it. I normalized this vector and multiplied by a scalar for constant speed when hitting the ball. Lastly, I just set the ball's velocity to this vector. The last thing I needed to do was to add prediction lines for how the balls were going to collide. I've already coded a collision handler function for physics, so I can use that again here, but to predict velocities instead of applying them. There's something in video games called a line trace, where a single invisible line fires in one direction and returns any object it touches. Using the same logic as launching the white ball, I can cast a line trace to detect any potential collisions in the ball's path. If the trace collides with anything, it also returns the exact position vector. Thus, using the white ball's position and the in position returned by the line trace, I can draw a small cylinder to signal the possible path of the ball. The tricky part for reusing the collision handler for physics is that this function takes objects as parameters. Since we want to predict where the balls would go, the objects or the balls themselves don't actually have any velocity yet. Therefore, we need to create temporary objects with the correct position and velocity vectors to simulate a collision. The velocities are easy to simulate. The white ball's velocity will just be the difference between the trace hit location and the white ball location. We can also assume the other ball to have a velocity of 0, since the player can only hit the white ball when all balls have stopped moving. Since the line trace will return the object, we can use the object.position syntax to find the ball's position. As for the white ball's position, we need to offset the hit location by the radius of the ball, since position vectors describe the center of the ball. The offset also needs to happen along the line trace, as that is the path of the ball. I achieved this by multiplying the normalized direction vector by -1 and the radius of a ball. I then added this vector to the line trace in position. Passing these through the collision handler function, it returns the predicted velocities. Lastly, using the same concept as before, I drew cylinders to represent their paths. I recorded my screen in slow-mo to ensure that this was working properly. There are some more things I added, so I just quickly run over them. The pockets are just hitboxes that destroy the balls when they collide with them, but the white ball respawns if it ever gets sunk. I also refined physics a bit because there was a bug where if a ball was too fast, it would just pass through the other balls without proper collision physics. I fixed this by having balls predict where their position would be in the next frame with a vector equation of their position, velocity, and delta seconds. This predicted position would be used to check for any collisions, and if any collisions did happen, the actual collision handler function wouldn't be called until half a delta second later, so it would seem more realistic.